Welcome to our explainer on rigid body mechanics. In this video, we'll dive into how solid objects move and interact in space. We'll start with the basics. What exactly is a rigid body? In physics and engineering, a rigid body is an idealization where the distance between any 2 points on the object remains constant, despite the forces acting on it. Understanding rigid body mechanics is crucial for designing everything from bridges and vehicles to robots and machinery. Throughout this video, we'll uncover principles of rigid body motion, explore the complexities of rotation, and examine the dynamics that govern their behavior. By the end of this series, you'll have a comprehensive grasp of how these concepts are applied in real-world scenarios, from calculating the stability of structures to designing moving parts. This foundational knowledge will empower you to approach problems in physics and engineering with greater confidence and insight. Let's get started. As we move forward, you'll see how these principles play out in various contexts and deepen your understanding of the physical world. Rigid body motion is fundamental to understanding the mechanics of solid objects. Unlike particle motion, which focuses on a single point, rigid body motion considers the entire structure, accounting for its size and shape. Imagine a solid object where every point within it moves in a fixed relationship to every other point. Whether it's a spinning wheel or a moving car, rigid body motion governs their behavior. Understanding this concept helps distinguish it from particle motion, where individual particles move independently. By grasping rigid body motion, we can better analyze complex systems in engineering and physics. As we move forward, you'll see how this foundational concept applies to specific motions, revolutionizing your perception of physical systems. Translational motion of rigid bodies occurs when a solid object moves along a path without rotating. This type of motion is simpler to comprehend compared to rotational motion, as it resembles how particles move. The key concept here is that every point of the rigid body follows the same trajectory, maintaining the same orientation throughout. The equations of motion governing translational movement are similar to those we use for particles. Whether we're considering acceleration, velocity, or displacement, the same principles apply, but we treat the rigid body as a whole unit. For instance, think about a car moving straight along a highway. Every component of the car moves along the same path, maintaining its orientation relative to the car's framework. To illustrate, we'll delve into equations of motion. These include Newton's second law, which states that the force acting on a rigid body equals its mass times its acceleration. We'll also see equations for displacement and velocity that follow basic kinematic principles. Understanding these concepts is crucial for analyzing real-world situations where rigid bodies are involved. As we move forward, you'll see how these equations describe straight-line motion and set the stage for understanding more complex scenarios involving rotational movement. Next, let's delve into the fascinating world of rotational motion of rigid bodies. This type of motion involves an object rotating around a fixed axis. For rigid bodies, it's essential to understand key parameters like angular velocity and angular acceleration. Angular velocity describes how quickly the object is spinning, while angular acceleration tells us how fast its rate of spinning is changing. Imagine a spinning top. As it twirls, its speed and changes in that speed determine its angular velocity and acceleration. Grasping these concepts is crucial for understanding more complex rotational dynamics. As we move forward, you'll uncover the equations that govern these motions and how they apply in various scenarios. In this segment, we delve into the equations of rotational motion, a fundamental aspect of rigid body mechanics. These equations are essential for understanding how forces and torques result in rotational acceleration. Just like in translational motion, where mass dictates how a force impacts acceleration, rotational motion depends on the moment of inertia. The moment of inertia is like the rotational equivalent of mass. It measures how an object resists changes in its rotational state. Another key concept is torque, which is analogous to force in linear dynamics. Torque causes changes in rotational motion, dictating how fast or slow an object spins. The core equations of rotational motion, much like Newton's second law for linear motion, relate torque to moment of inertia and angular acceleration, expressed as torque equals the moment of inertia multiplied by angular acceleration. Understanding these equations allows us to predict and analyze the behavior of rotating objects, from simple wheels to complex machinery. As we move forward, you'll see how these principles are applied in practical scenarios, enhancing our grasp of rigid body dynamics. In this segment, we're diving deep into the world of rigid body dynamics. What exactly is rigid body dynamics? It's the branch of mechanics focusing on how solid objects move under the influence of forces and torques. By applying Newton's laws specifically to rigid bodies, we can predict their motion with remarkable precision. We'll start with Newton's first law for rigid bodies, which tells us that a body remains in a state of rest or uniform motion unless acted upon by an external force. This principle helps us understand stability and the initiation of movement in rigid bodies. Newton's second law, perhaps more famous, connects force, mass, and acceleration. For rigid bodies, it extends to include rotational motion, linking torque with angular acceleration and moment of inertia. This is crucial for designing anything from simple wheels to complex machinery. Finally, Newton's third law, every action has an equal and opposite reaction, explains the interactions between different parts of a rigid body system. These principles are not just theoretical, they have practical applications in engineering, from constructing bridges to designing vehicles. As we move forward, you'll see these concepts applied in real-world scenarios, illustrating the importance of rigid body dynamics in our daily lives. As we delve into the world of rigid body mechanics, it's essential to see how these principles are applied in everyday life and engineering. From towering skyscrapers to the vehicles we drive, rigid body mechanics form the backbone of modern design and construction. Engineers rely on these principles when designing machines, ensuring they can withstand forces and operate efficiently. In our daily lives, every structure we interact with, be it bridges, houses, or household appliances, exemplifies the importance of rigid body mechanics. Understanding these applications not only highlights the vital role this knowledge plays in building our world, but also demonstrates its significance in finer design details. The precision required in engineering applications underscores the importance of mastering rigid body mechanics. As we move forward, you'll see common problems encountered in this field and how to solve them, further solidifying your grasp on these fundamental concepts. Stay tuned for practical insights that will equip you to approach and overcome these challenges. Let's dive into some common problems in rigid body mechanics and explore effective solutions. Understanding these challenges will not only enhance your grasp of the subject, but will also prepare you to tackle real-world issues. One frequent problem involves determining the forces acting on a rigid body in equilibrium. To solve this, start by drawing a free body diagram, isolating the body and identifying all the forces and moments acting on it. Next, apply Newton's laws and use the equilibrium conditions, summing forces and moments to zero. Another common challenge is analyzing the rotational motion of a rigid body. Begin by identifying the axis of rotation and calculating the moment of inertia. Then, apply the rotational analog of Newton's second law, relating torque, moment of inertia, and angular acceleration. To illustrate, consider a beam balanced on a fulcrum. By breaking down the forces and applying the principles we've discussed, you can derive equations to solve for unknowns and understand the system's behavior. As we move forward, you'll see how these problem-solving techniques are applied in various scenarios, helping you build a solid foundation in rigid body mechanics. As we conclude our exploration of rigid body mechanics, let's recap the key concepts we've covered. First, we delved into rigid body motion, understanding how solid objects move in a fixed relationship to their points. Then, we focused on rotational motion, exploring how objects spin around an axis and the importance of angular velocity and acceleration. Finally, we examined the dynamics of rigid bodies, applying Newton's laws to predict how forces and torques affect their movement. These concepts are fundamental to many physical systems and form the foundation for advanced studies in physics and engineering. Understanding rigid body mechanics is crucial for solving real-world problems in design and engineering. By mastering these principles, you equip yourself with the tools needed to innovate and excel in numerous fields. This wraps up our summary of rigid body mechanics. Thank you for joining us on this journey through motion, rotation, and dynamics. In the next segment, we'll encourage you to take your learning further, offering additional resources and ways to stay engaged. Stay tuned and keep exploring. Thank you for watching our explainer on rigid body mechanics. We hope you found it insightful and engaging. If you enjoyed this content and want to dive deeper into the world of physics and engineering, don't forget to like this video and subscribe to our channel. By subscribing, you'll stay updated with our latest educational videos, helping you expand your knowledge further. Also, be sure to check out our related videos where we explore more fascinating topics in rigid body motion, rotation, and dynamics. Your learning journey doesn't have to end here. Continue exploring with us. Thank you for your support and happy learning.